This is definition of moments of inertia for areas. So if we had an axis of z, x, y, and we had a plate submerged, saying that xz is a water plane, then we're going to have a distributed pressure along this plate. And that's going to go along the whole area of the plate. There you go. And this pressure is going to be equal to the specific gravity times y. And if we wanted to take a differential area of this plate, so dA, we would apply dF at that area, and that would all be at distance y from the xz plane. So we would know that dF is equal to the pressure times the area, the differential area, and that pressure is equal to the specific gravity times y times dA. And if we wanted to take the moment about the x-axis, then we would have the differential moment times y times dF, where dF is equal to the specific gravity y squared dA, such that your moment is equal to the integral of your specific gravity y squared dA. And this quantity of the integral of y squared dA is called the moment of inertia, Ix. Okay, so let's look more at this moment of inertia. So, Ix is equal to the integral of y squared dA. Iy is equal to the integral of x squared dA. These are both over the area. And now, if you took dA about the pole O, or the origin, or z-axis, it gives you the polar moment of inertia. Which is JO equal to the integral over the area of r squared dA, which is really just equal to Ix plus Iy. And r squared is equal to x squared plus y squared. So Ix, Iy, and Jo are going to have units of length to the fourth. Such as meters to the fourth, millimeters to the fourth, inches to the fourth, and so on. Okay? So the other thing we need to understand is the parallel axis theorem for an area. So if we had our axes, xy, and some area like this, and our centroid is going to be right here. So if we put a axis right through that centroid, we'd have x prime and y prime. And if we were looking at a differential area, that would be located at y prime and x prime. And this distance from the x-axis to the centroid, that's going to be called dy, this one dx, such that the total is d. So if we are looking for Ix, it's going to be equal to the integral over the area of y prime plus dy. That's all going to be squared multiplied by the differential area. So if we multiply this out, we get that Ix is equal to the integral of y prime squared dA plus 2 dy times the integral of y prime dA plus dy squared times the integral over the area of dA. And this becomes 0, such that we're left with Ix is equal to Ix prime plus a dy squared, which is just your moment of inertia about the x prime axis plus your area times the distance from your x-axis to your centroid, dy. So the same thing holds true for Iy. That's going to be Iy prime plus a dx squared. And Jo would be equal to jc, so about the centroid, plus a d squared, this distance d. So what that theorem is telling us is that the moment of inertia for an area about an axis is equal to its moment of inertia about a parallel axis passing through the area's centroid plus the product of the area and the square of the perpendicular direction between the axes. So let's write that out. The moment of inertia for an area, excuse me. There you go. The moment of inertia for an area about an axis is equal to its moment of inertia about a parallel axis passing through the area's centroid. Plus the product of the area and the square of the perpendicular distance between the axes. The next thing we need to define is the radius of gyration of an area. And the radius of gyration is used for the design of columns in structural mechanics. So that's defined as kx is equal to the square root of ix over a, ky is equal to the square root of iy over a, and ko is equal to the square root of jo over a. Okay. So now let's look at how we would solve these problems. How would we solve for the moment of inertia? So there's a table in the back of your book for some common shapes. So if we were to look at the rectangle, and we had our x and y axes going through the centroid, we would find that Iy is equal to 1/12 hb cubed, and Ix would be equal to 1/12 bh cubed. So this is your base, and this is your height. Alright, so let's look at what happens when you can't just find it in the back of the book. Say we had an area that looks something like this. And this area has a line where y is equal to a function of x. So just like when we were doing the centroid, we can draw a rectangular differential element. So this is going to be my dA, the height is going to be dy, and the base is going to be x. And the centroid of this differential element is going to take place at x over 2. And the height is going to be y. So, if I were looking for Ix, my differential element is parallel to my x-axis, so I can use the formula, the integral of y squared dA. And in this case, dA is going to be equal to x dy, such that I plug that in, y squared x dy. And I can use the limits of integration as well as this to solve for what Ix would be. But if we were using the same differential element to solve for Iy, we would have to look at it differently. Because the centroid of this thing, it always happens at y. But if you were going over this entire element, the centroid moves, the moment arm moves. Yeah, it's the moment arm. The moment arm moves along, such that you need to be using the parallel access theorem, because the centroid is actually located here. So, In that case, I'm going to take the differential of IY, which is equal to DIY prime plus dx squared dA. So, this rectangular differential element can be determined from what we learned up here. So I'm looking for IY, so I can say that's 1/12 times the height, which is dy, times the base, which is x. And then my dx is going to be this distance to the centroid, so that's x over 2. And that's all squared, times dA, which is x dy. And this adds together to be 1/3 x cubed dy. So if we take the integral of both sides, we get that IY is equal to the integral 1/3 times the integral of x cubed dy. So that's how you have to solve it when your rectangle is perpendicular to the axis that you're trying to find the moment of inertia about. So let's look at it the other way. So I've got my same xy axis with my same area. Y is equal to a function of x. But in this case, I'm going to use a vertical differential element. So this has a width of dx and a height of y. And this distance to the centroid of this rectangular element is y over 2. So in this case, our dA is going to be equal to y dx. So if I'm looking for IY, the element is parallel to my y-axis, so I can just use the formula, the integral of x squared dA. If I put in what I have for dA, it'll be the integral of x squared y dx. And now, if I want the moment of inertia about the x-axis, the differential element is perpendicular to the x-axis, so I need to use the parallel axis theorem, such that I would get d I x prime plus dy squared dA. So we're looking for Ix of this rectangle, and Ix is equal to 1/12 times the base, which is dx, times the height, which is y cubed. And over here we've got dy, which is y over 2 squared, times dA, which is y dx. And those combine together to be 1/3 y cubed dx. We take the integral of both sides such that we get that Ix is equal to 1/3 times the integral of y cubed dx. And that's it.